All right, everyone. Welcome to this inaugural seminar. Let's give people a few minutes and then we can begin formally. We'll begin formally in a couple of minutes. We will begin in exactly 1 minute. All right, everyone, let's begin. First of all, I would like to thank all the participants for being here. In particular, Sarmat is here, and thank you, Sarmat. I'm sure Waqas will appreciate you coming in. I'll begin by introducing the speaker. Professor Waqas Masood is currently the chair of the physics department at ComStats Islamabad. Waqas has been actively engaged in research in the field of theoretical plasma physics for the last 15 years or so, and has published more than 135 international papers in excellent journals. He's won quite a few accolades for his work. He was awarded the Salam Prize in 2009 and the Presidential Award for the Pride of Performance in 2011. He's been very active on the national scene and has been on the technical and organizing committees of many scientific conferences. He's also been actively involved in teaching at various levels in schools and workshops for science students and faculty training programs. He obtained his PhD from Queen Mary and Westfield College, University of London. He's a dear friend and a great speaker. Please welcome Waqas Masood.
Hi, everyone. Afternoon, and many thanks, Rizwan, for this very wonderful introduction. So I just share screen. So, can everybody see this? If yes, then we can.
Yes, we can.
All right. Okay, and I'm very glad that Sarmat is also here. So, a very warm hi to Sarmat. So today I'm going to talk about the exotic features of the fourth state of matter in the high entropy region of the terrestrial magnetosphere. So fourth state of matter, I mean plasma physics, and I'll shed light on this, why it is called the fourth state of matter. So the idea is to introduce you guys, because I've been told that the audience has both undergrad and grad students. So at times I'll be slightly more technical, but most of the times I'll try and not to show too many equations and basically just explain the physics that those equations which I'm not going to show represent. So the layout of this talk is that I'm going to first define what plasmas are and what are the basic criteria, what is the basic criteria, and that differentiates an ionized gas from a plasma. And then how do we, because generally I, study the wave propagation in plasmas, both the linear propagation and the nonlinear propagation. Of course, this particular talk does not talk about the nonlinear wave propagation. So we'll stick to the linear wave propagation, but of course at a different level. And then because I've been interested in space plasmas, and I got my degree in space plasma. So I'm going to talk about the Sun-Earth interaction. And in that, I'm going to talk about the various regions of, solar terrestrial interaction, which are of interest. And then as an example of the kinds of applications that plasmas have, I'll briefly introduce the 4-cluster spacecraft, and then a bit of theory and data analysis of a particular kind of wave in plasmas and in a particular region. And finally, I'm going to talk about the generalized RQ distribution, first by showing you that what the data tells us about the kind of electron distributions we have downstream of the bow shock. I'll introduce all these terms, what is a bow shock and all that. So in the end, it will all make sense, and I hope that convince you that all is told to you in a very sequential fashion. Okay, so to begin, fourth state of matter. So plasma is basically an ionized gas consisting of positively and negatively charged particles. And the fundamental trait it exhibits is the quasi-neutrality. So it means that the number of ions are almost equal to the number of electrons, but of course, they aren't exactly equal because you need, plasma is an electromagnetic medium. So So that there shouldn't be for total charge balance, otherwise it will be a neutral gas, right? So I need slight imbalance. So the slight imbalance is all the beauty. And so the plasmas can be created in many ways, but the way generally for the beginners who are not familiar with plasma physics, so when you heat a solid, you get a liquid. When you heat a liquid, you get gas. And if you heat the gas further, you get the so-called fourth state of matter called plasmas. So in all the visible universe that we know of, 99% contain plasmas. Earth is a special place because we do not have very high temperatures. So of course, we do not come across plasmas here, though they can be created in the laboratory, and we do create that. Fusion physics is one fascinating aspect of plasmas. So why this fourth state, why this term was coined? Because the ionization process starts at a well-defined temperature, usually a few thousand kelvins. A plasma is often referred to as the fourth state of matter. And so again, it tells you that it can be produced in many different ways. But without going into that, I would like to just tell you that what is the difference between an ionized gas and a plasma. So first things first, every plasma is an ionized gas. However, every ionized gas is not a plasma. So there are three basic criterion that differentiate a plasma from an ionized gas. But before these terminologies make sense to you, what this lambda D and ND and omega P and omega C are. So just let me tell you how the plasma is created. So you have, gas containing, let's say, protons and electrons, and now you subject it to an electric field, the charge separation will be created. And because of that charge separation, now you basically, it's a non-equilibrium situation, and nature detests deviation from the equilibrium, and it wants to restore its equilibrium posture. So how does that happen? In this particular case, electrons, as you know, there's a 3 order of magnitude difference between electrons and ions. So electrons being tenuous, they rush to restore the neutrality, but because of their inertia, they exhibit a to and fro motion, and this to and fro motion is a frequency which we call as the plasma frequency. And the distance that the plasma takes when it is subjected to an externally applied field, or maybe in an open system from anywhere. So the time it takes to ward off the potential, that length is called the Debye length. So this lambda D is the Debye length, and omega P is the electron plasma frequency. So those of you who have done their undergrad, so they know by now that this kind of frequency develops when you have an oscillator type equation and a second order differential equation. And so I have omitted the mathematical details, but by solving the Poisson's equation, one can get the expression for the lambda D. The basic catch, the idea here is that when you have plasma, then the potential is warded off quickly. There's an exponential decay. So there's an e raised to minus r over lambda D. But without getting into that, so the first criteria, it says that the Debye length ought to be much smaller than the size of the system under consideration. Why is that? Because plasma has to exhibit quasi-neutrality. So the minimum distance I've just told you for taken by the plasma to restore its quasi-neutral posture is lambda D. So this means that the plasma is defined outside the Debye sphere. Generally, we draw a sphere around this thing, the length that we associate with the restoration of the quasi-neutrality posture. So outside the Debye sphere, plasma exists. Inside the Debye sphere, there are just fluctuations, and we cannot call this stuff inside as plasma because there are fluctuations and quasi-neutrality is violated. So this is the first criteria. So if I have a lambda D, which is longer than the size of the system under consideration, then by all practical purposes, I cannot qualify it as a plasma. because then it is not a plasma, because plasma has to exhibit quasi-neutral posture. The second thing is slightly more tricky. From the statistical perspective, I can always say that in order to describe something statistically, I ought to have a very large ensemble. Why do I have to have a large ensemble? Because you know from your basic statistical mechanics that the standard deviation varies inversely as the square root of the number of particles. So if I have a very large ensemble, then of course the fluctuations are small and I can accurately describe the average quantity. Because in plasma, we deal with the average quantities, so we ought to have a very large number of particles. So that's the statistical argument. The other thing is that if we do a bit of other argument, we can also show that what it tells us is that E phi over KTE is much, much less than 1, which means that E phi is the potential and KTE is, of course, the thermal energy. So what it says is that plasma is primarily a kinetic medium. So this particular statement, I don't want to show the proof here, but this is also a statement which from the plasma perspective is a more pertinent statement, is that the potential forces are much weaker than the kinetic forces, and plasma essentially is a kinetic medium. And we call this kind of a system where E phi over KTE is much smaller than 1, a weakly coupled system. So TE comes here because it's the electrons being tenuous which play a role, in restoring the quasi-neutral posture or restoring the equilibrium, which is disturbed by the applied potential or some potential that arises from somewhere. And the other thing is that plasma has these ions and electrons. So if the recombination rate is very high because of the collisions, then of course it will become a neutral gas. So this is a natural requirement that the plasma frequency ought to be much greater than the original frequency, else it will be a neutral gas and no interest to us. So these are the three. So at the moment, what I've talked about is an unmagnetized plasma. It is for the beginners, it's kind of hard to tell that magnetized, unmagnetized, cold, hot, these are all very relative terms. It depends on the kind of spatiotemporal scale you are looking at things. So I'll try and make more sense of this in the next slide so that I put the message across that it's a game of approximation. What you call magnetized, unmagnetized doesn't mean that you don't have a magnetic field. You have a magnetic field, but you can always look at things on a spatiotemporal scale where the magnetic fields can be ignored. And similarly, plasma is hot. I've just told you it's primarily a kinetic medium, but then you can go to a scale which is where, with respect to some particular velocity in the system, it is either less or greater, and that determines whether the term hot and cold can be used or not. So one more thing that I would like to say here is that all the beauty of plasma physics lies in the fact that you have two species, ions and electrons. Although we have multi-component plasma and things would be different over there, some kind of new physics would arise. But at the moment, I'll just focus on electron-ion plasmas because space plasmas are generally electron-ion plasmas. So the mass difference between the electrons and ions, that is the basic beauty of plasmas. That is what makes it so incredibly complex. But there are many models to study plasmas, and I'll tell you where this differentiation is kept and where it is ignored for a little while because it works surprisingly in many cases. So why I was telling you this was that naturally ions being massive have their own spatiotemporal scale, and electrons being tenuous, they have their own spatiotemporal scale. So it depends what you are looking at, how you are looking at it. So you can make things quite easy and you can make things incredibly complex. So let's move forward. And So plasma models. So the most simple picture is the single particle motion. So, well, you can ask that plasma is a combination of charged particles. So what do we mean by single particle motion? So it is very helpful because you need to know how the charged particles behave when they are subjected to constant electric and magnetic fields, spatially varying electric and magnetic fields, time varying electric and magnetic fields. So once you know that, then whatever picture you employ, the charged particles are going to, show the same behavior. So you already know through single particle motion that how the charged particles behave. So this type of theory is called the orbit theory. Why it is called orbit theory? Because it has a certain scaling. So when you have a magnetic field, you know when a charged particle is subjected to a magnetic field, a uniform magnetic field, it executes circular motion. And that circular motion has a radius. That radius we call it as the Larmor radius. There are so many other terms, gyro frequency, and similarly, we will have gyro radius. And so spatiotemporal scales arise like this. In an unmagnetized plasma, you have the device screening and the electron plasma frequency. But when you have a magnetized system, then you will have the new spatiotemporal scales, which is the Larmor radius and the Larmor frequency. So this orbit theory says that the Larmor radius is much smaller than the scale of the system under consideration. And the other thing it says is that during one gyro motion, whatever is changing in the system is not felt. So what it means is that if I'm considering some kind of spatial or temporal change, it is felt over many, many gyro periods or gyro motions. It is not felt in a single gyro period, which means that these changes are very slow. And from Hamilton's Jacobi theory, you know that this gives rise to the concept of adiabatic invariance. And of course, in the orbit theory, we see the three adiabatic invariants. This one is mu, and then magnetic moment conservation and flux conservation. So I'm not going into the details of that, but the single particle motion basically deals with the fact that you have these scalings that RL over L is less than 1, and the changes that you are going to consider are going to be very small, and they're not going to be felt in one gyro period, but over many gyro periods. So this theory is intimately linked with Alvin's concept of varying center motion and the adiabatic invariance. So that is all. Just for those who want to dig deep, of course, they can study the subject and learn more. Here, I will just say what it says. The next thing, the first theory where we actually now take charged particles, electrons, and ions is a single fluid theory. And what we mean by a single fluid theory is it is a theory where we still do not entertain the mass difference between the two species, and we create a sort of a center of mass system where we define an average velocity, an average mass, and everything. So it becomes a single fluid theory. And as I've told you that there's a 3 orders of magnitude difference between the ions and electrons. So ions, of course, the ion gyro frequency is going to be much slower than the electron gyro frequency, and ion gyro radius is going to be much larger than the electron gyro. So this theory is applicable because every theory has applicability in a certain scale. So this theory can be useful when I look at the frequencies which are much smaller than the ion gyro frequencies, and the length scales which are much greater than the ion gyro rates. So this theory has been employed very successfully to explain the large scale, physics of Sun-Earth system, what we call the Sun-Earth system, solar terrestrial system, whatever you may call it. So this is the applicability criteria for the single fluid theory. It is So now that I add up everything, so one important aspect is that you can't define a current here, because current is NIVI minus NEVE and multiplied by E. But now there is no distinction between VI and VE because you have defined, combined V. So it can only be explained through the Ampere's law, because del cross B is mu naught J. So current is only defined through. So there is no concept of current in a single fluid theory. So these are just because there are grad students here. I don't know whether there is any grad student of plasma physics, but this is just for their consumption. That these are the things, the technical details that one needs to know, about single fluid theory. Then comes the multi-fluid theory. One thing that I would like to say here, I would like to actually switch to the board now and show you something which I would like to show. So if I just as we know that since we have we have one square, then I can write. I'll tell you what this equation is. Do I need to be louder? Can anybody hear me? Yeah, because I need to know. What I'm going to do is that I'm going to just write up my question and then to explain what it means.
Waqas, हेलो, आपकी आवाज एक तो थोड़ी सी थोड़ा सा मसला आ रहा है आपकी आवाज में. दूसरा
Can you hear me now?
जी, आप बेहतर है.
So just bear with me for a moment. I am going to write down these equations and then I'll explain. And in the meantime, I will not talk, right? So I just I'll write something.
ठीक. Sarmad, you want to ask a question? Sarmad,
All right. So what I have just written over here, the first equation is what we call as the Masow's equation. This is nothing but statement that df over dt is equal to 0. And this is a statement of the conservation of phase space density as well. So we start from this, and this is f is a distribution function. And of course, it depends on x, y, z, vx, vy, vz, and t. And because it's an electromagnetic medium, the acceleration is f over m, and f is q into e plus v cross b. Now I need to tell you, what do I mean by a fluid theory? So I just wanted to tell you first that the number density is defined as the integral distribution function over the, phase space. Over here, I just write d cube v because it's a distribution function. So generally, the distribution function is just, let's say Maxwellian distribution is just a function of velocity. So but in general, if I integrate this over d cube p and d cube r, I'm going to get a quantity which is dependent on just position and time. So it means that the velocity information has been integrated over. On the contrary, in the first equation, which is the Vlasov equation, I have a distribution function, and that is defined in phase space. So over there, the information and velocity is there, So it has not been integrated over. That is all that I wanted to say. And now I'm coming back to what I'm going to tell you. So fluid theory deals with phenomena where you look at the quantities which are a function of space and time. On the contrary, the kinetic theory of plasmas deal with the information about the velocity space as well. So the difference between the fluid theory and the kinetic theory is that the velocity distribution information is very important in kinetic theory, but in a fluid theory, velocity distribution is integrated over, and you look at things which are varying with space and time, and you write down the conservation laws like the density conservation given by the continuity equation, then you write down the momentum conservation equation, and if need be, you write down the energy conservation equation, coupled with, because it's an electromagnetic medium, so you will have the Maxwell's equations. And depending upon what type of wave you are looking at, you will employ either the, Gauss's law, and then you will, if you are looking at an electrostatic wave, you will have a Poisson's equation, and if you're looking at an electromagnetic wave, depending on stuff that you're looking at, you will either use the Faraday's law or the Ampere's. So that is what I want to tell you. The example that I have chosen to tell you here later on is an example from the kinetic theory. So it means that the details of the distribution function are very important. And one thing that is beyond the realm of fluid theory is that it cannot tell you about the wave-particle interaction. Kinetic theory of plasmas can tell you, because wave-particle interaction means that the wave can give energy to the particles. So this can be, and then the kind of theory that I'm going to use is the linear kinetic theory. What it means is I'm going to tell you how a wave can give energy to the particles, but I cannot tell you what is going to happen to the equilibrium distribution function, which is F0. I'm just going to tell you about the wave-particle interaction, but not what has happened to the equilibrium distribution function after the wave has imparted energy to the particles. So for that, you need to go to the quasi-linear kinetic theory. And then if you want to take everything, sorry, please.
Sorry, there's a question. Someone has raised hands. Awais, yep. If you want to ask question, just go on. Yeah. Unmute yourself and ask question. Abhi unmute nahi kiya aapne. जी कहिए.
Yeah, so sir, is the quantum is the जो plasma model है, ये quantum field theory से formulated है, means कि आप इसको quantum field theory से produce कर सकते हैं this plasma model.
देखिए यहाँ पे तो जो हम बात कर रहे हैं वो तो सारी क्लासिकल है, बिकॉज आपका जो सारा एक्सटेंट है सिस्टम का, क्वांटम से आप किसी भी चीज को क्वांटम तब कहेंगे जब आपका इंटर पार्टिकल डिस्टेंस जो है और de Broglie वेवलेंथ जो है वो आपस में कंपैरेबल हो. यहाँ पे तो ऐसा कोई इम्कान ही मौजूद नहीं है. अगर आप सिस्टम को बहुत स्क्वॉश्ड अप, these are very tenuous plasmas, these are very low density, high density, high temperature plasmas. यहाँ पे जो आपके पास पार्टिकल पर सेंटीमीटर क्यूब है वो 5 है. आपके पास जो बहुत जबरदस्त वैक्यूम लेबोरेटरीज में होता है वो भी 14-15 पार्टिकल्स पर सेंटीमीटर क्यूब है. यहाँ पे 5 particles per centimeter cube है, लेकिन क्योंकि the spatial extent of the system is very large, so you can call it a plasma. ये बहुत ही tenuous system है. तो यहाँ पे तो quantum का जिक्र, quantum plasmas वहाँ हो सकते हैं जहाँ पे the system is very, यहाँ पे number densities are very high, of the order of 10⁻26 number per centimeter cube. यहाँ पे तो 5 particles per centimeter cube आपके पास number density है. तो जो quantum system है वो तो यहाँ पे space plasmas are classical plasmas. Astrophysical plasmas are generally quantum plasmas because the number densities that you deal with are very, very large. And because of that, it's kind of like now a pretty much squashed up system. So now the de Broglie wavelength becomes comparable with the interparticle distance. It's just like when you employ the Maxwell-Boltzmann statistics and when you employ the Fermi-Dirac or Bose-Einstein. It's just the same criteria, right? So interparticle distance and the de Broglie wavelength matters here. So this, for all practical purposes, is a classical system.
Yeah.
I hope I have
Thanks.
answered your question.
Yes.
And I don't know quantum field theory, by the way.
Yeah.
Rizwan will give me private tuition on that. All right.
Yeah.
Okay.
Thank you.
Okay, Ji, moving on. Okay.
Hey.
All right, so here we go. So I'm going to talk about Sun-Earth interaction. So I need to start with the fact that Sun is the king, the star, and the planets are gravitationally bound to it. And of course, at the moment, we are looking at just the Sun-Earth. And just for the sake of information, that Mercury, Venus, Earth, these are called the inner planets, and the outer planets are Jupiter, Saturn, Uranus, Neptune, because of their size. And they have got massive size because they were further away from the sun. They're also called the Jovian planets. And a little comment that Pluto, when I gave a talk many years ago about this kind of thing, Pluto was, a planet, but now it has been relegated to the status of a dwarf planet because according to the new definition, it is, it has not been able to clear its neighborhood. So it means that it orbits around the sun. It has the mass to have, a circular structure, but it doesn't have the gravitational pull so that it either sucks everything inside or it pulls things apart. And there shouldn't be any planet of the same size or structure of the same size. So it doesn't qualify that now. So it has been relegated to the status of a dwarf planet. So anyway, we are concerned about Sun and Earth interaction. So I need to tell quite a few things about Sun. So there are many ways that you can look at the Sun. From the astronomical perspective, if you just read about Sun, so it's a G-type main sequence star. So main sequence, you need to know the Hertzsprung-Russell diagram, and then you need to know what is a G-type sequence. You need to know the Morgan-Keenan system, which says how hot something should be to be in this category or that category. And then, of course, it has a massive gravity, and every star is born and every star has to die. And depending on the Chandrasekhar's limit, you know that how a star is going to die. So this sun of ours is going to die as a white dwarf because of its mass. So there are many perspectives from which sun can be seen, but from the plasma's perspective, I'll tell you what is it that we need to know and what we are interested in. So there is fusion going on in the core of the sun. So that is one thing. And it has a magnetic field because of the dynamo effect, because there is this electrically conducting fluid which is rotating inside the core of the sun, and that is generating a magnetic field. And that's why it has a magnetic field. And of course, there are many layers of the sun. The outermost is corona. So without delving deep into that, I just want to tell you about the magnetic field, because that is one important aspect of what I'm going to tell you next. So looking at the magnetic field, it is tightly wound around the equator, and then the magnetic field lines around the poles, they take a longer time to close upon themselves. So what essentially it means is that it is stronger around the equator and weaker at the poles. So that's the way the structure of the magnetic field is, a dipole structure. So, and one more thing, that sun rotates. So you can take a radial motion, but you can also, because it has a garden hose pipe effect, So it is generally referred to as a Parker spiral. I'll tell you when I'll talk about the solar wind, but first I need to convince you that sun is a magnetically very active region. So here comes the first, evidence that it is magnetically very active. So these are sunspots. Sun has a solar cycle of roughly around 11 years. And so when sun is magnetically very active, then the number of sunspots begin to increase. And sometimes people measure the activity of the sun through the number of sunspots. So the increased sunspots means the sun is in active region. It becomes dormant at times, but at times it becomes magnetically very active. And that is the time when you see a lot happening on the Earth too, but that story a little later. So sunspots are manifestations of magnetically disturbed conditions at the sun's visible surface. So they are somewhat cooler than their surroundings. And that is why you see these dark patches. So the darker means if you look at the sun, you will have these very bright spots, and then you will have the darker spots, and these are the cooler regions called the sunspots. Then the little details that I'm going to skip. Now the next thing that is the solar flares. So these are the observations, that tell you that sun is magnetically very active. So solar flares are huge explosions on the surface of the sun. They were first observed by Carrington and Hudson in connection with the Great Aurora of 1859. So now these are very fast processes with timescales of only a few minutes. And they are thought to be formed as the sunspot-related magnetic fields. Okay. The next thing is the coronal mass ejection. Now, coronal mass ejections are more violent events, and these are longer events. They carry on over the course of several hours, unlike the solar flares, which last a few minutes. And they are associated with the prominences. And this is, how the coronal mass ejections look like. Okay, so just to tell you that sun also has a magnetic, Earth also has a magnetic field, because I'm going to talk about, because again, the dynamo effect is there. There is a magnetic field. And of course, it's tilted, that we know. Okay. So this is the traditional picture of the Sun-Earth interaction. This is an artist's impression of Sun-Earth interaction. Of course, these are all artistic lines. You can't see them. Fields are not visible. This tiny thing over here is, do I have pointer? Yeah. Oh, yeah. So
you can right click and choose a pointer.
Right click. Okay. So let me go back. Yeah. So can you see this is Earth and this is Sun, and
Can you guys?
Yes, we can. Yeah.
okay. So Parker, before the advent of the space age, conjectured using the fluid model that because whatever the atmosphere of the sun is not in equilibrium with the outside atmosphere, so there he predicted that there will be a stream of charged particles coming out of the sun, which he coined as the solar wind. Okay, I always say that it's remarkable that he has not been awarded the Nobel Prize, because the satellites didn't go in space and there was no observation, and Parker predicted a year before that there will be a solar wind, and then the satellites confirmed that there is solar wind, and all that we are going to talk about, solar wind plays a crucial role in that. So there's for you to know that there is an outflow of charged particles coming out from the sun. But before that, I need to move forward. I'll come back, but I need to tell you. So first things first, I told you that the magnetic field is very tightly wound around the equator, and it is weaker around the poles. So what we have seen is that the solar wind that comes out of the equator has less velocity and speed, but on the contrary, around the poles, its speed is much larger. So it's like 100 kilometers per second from the equator, and something like 400, in fact, 700 kilometers per second from the poles, and the average is 450 kilometers per second. Solar wind average velocity is 450 kilometers per second coming out from the sun. So this is a snapshot of the Ulysses. These are the typical solar wind parameters, but I wanted to show you this Parker's solar wind equation. So it's just an equation from the fluid model, and just using the slopes and a bit of balance between the thermal energy and the gravitational pull, you can tell that there will be a stream of particles coming out from the sun. And I'm not going to talk about this, but I'm going to first tell something else. Okay, so you know that Faraday's law is del cross E is minus curly B over curly T. So if you use the Ohm's law, which is J is equal to sigma E into V cross B, and you just do a bit of mathematical manipulation, then you will come up with this magnetic induction equation, which is given by del cross V cross B plus 1 over mu naught sigma del square B. So the first term is the convection term. As you can see, it contains the velocity. So there is a stream of particles coming out from the sun. And the other thing is del square B, which has to do with the diffusivity of the magnetic field. So outside the sun, the infinite conductivity approximation holds. So it means that I can do away with the second term. I can do away with the second term. And all that I will have is the del cross V cross B. And when I have curly B over curly T as del cross V cross B, we call it the frozen in flux assumption. And what it essentially tells you physically is that wherever the fluid goes, the field is dragged with it, or wherever the field goes, the fluid follows it. So what it tells you is that the solar wind comes out of the sun, and along with it, it drags the sun's magnetic field, and then it permeates all space, and what we call the interplanetary magnetic field, all permeating, is nothing but the sun's magnetic field, which has been dragged with the solar wind due to the frozen in flux assumption at the sun surface. So that is all that I wanted to tell you, but I wanted to convince you more. I didn't want to utter it. I wanted to show you that through equation, I can show you that. So that's the power of the equation, simple looking equations, but very powerful in terms of the physics that they imply. All right, so I'll come back to these a bit later. I need to tell you one more thing. Okay, another thing that I want to tell you is that there is this, if you do the order of magnitude analysis of the two terms on the right-hand side, the first is the convective term, the second is the diffusive term. Then the order of magnitude analysis means that you have the curls and everything you ignore. You just say del is 1 over L, and once you do that, what you get is mu naught sigma VL. And mu naught is a constant, sigma is conductivity, and V and L. So flow speed and the scale length, these are the important parameters. So when the velocities are very large and scale lengths are very large, the magnetic Reynolds number is going to be extremely large. And it means that for all practical purposes, I have a frozen in flux assumption. But if the velocities are slow and I come across boundaries, then of course the second term is going to dominate, and I'll tell you later the spectacular role that it plays. So bear with me. I need to tell you a long story, so but I need to tell you some physics behind it so that you understand what I'm trying to say. Now, one more thing, coming back to the fluid model, I told you for large scale structures, MHD model works very well. So if you throw a pebble in a pond, circular waves appear. So if you have a plasma as a pond, and if you throw a pebble or you create a perturbation, then you will not have circular waves. You will have three types of wave, what we call as the acoustic waves, and the Alvin waves, and the magneto-acoustic waves. So these are the three waves that you will see in a plasma pond if you have an MHD model. These are the simplest. From a simplest model, these are the three waves that you get. As you make the models considerably complex, you will have a zoo of plasma waves. So I am not going to talk about that, although at some point I need to tell you a bit about it. All right, so the story goes like this, that you have now a plasma, because solar wind is a plasma, it qualifies to be a plasma. All the plasma criteria is satisfied. So the linear wave, the solar wind speed is 450 kilometers per second. There is no linear wave that tells you that is like faster than this if you just put in the parameters and calculate the frequencies. So the Earth has a magnetic field, I have told you. Now, just like a river, water is flowing and it encounters a large rock, so the flow will be around it. But here, there is an obstacle of the Earth's magnetic field, and something has to tell the solar wind that there is an obstacle of Earth's magnetic field along your way. Now, the linear analysis cannot do that, but because the linear waves cannot propagate that fast. Solar wind is much faster than that. So then you have to have something which is nonlinear, which should give rise to a system that reduces the velocities of, in fact, the velocity of the solar wind below the plasma linear velocities. So that is done by the, what we call this purple colored bow shock. So bow shock is in the Earth's magnetosphere. For those who want to know about it, this has been created through the Sajanico models. So this is another thing that I want to tell you, that there are collisional plasmas and there are collisionless plasmas. So we call collisionless plasmas when the mean free path is much larger than the size of the system under consideration. So for instance, the thickness of the bow shock is 100 to 1,000 kilometers, whereas the mean free path calculated from the gas kinetic theory is of the order of 1 AU, which is 93 million miles. So you can see that for all practical purposes, the Sun-Earth system and the plasmas that we are encountering are collisionless plasmas. So this is a collisionless system. So we have a collisionless shock. We can't produce this shock through the collisions of particles. This is created through wave-particle interaction. And kinetic theory comes into place, of course, that one needs to know in order to understand why this shock is formed. But just to understand, now you understand that the primary purpose of this bow shock is to bring the solar wind velocity below the velocity of the linear waves of plasma. So how does it do that? MHD equations I have told you are nothing but the conservation equations: density conservation, momentum conservation, energy conservation. Since it's a charged fluid, it is coupled with the Maxwell's equations, and this system is called the Rankine-Hugoniot system. And if you solve it, then you find that the density goes up, the field goes up, and the velocity comes down. That's the primary job of a shock. So in order to convince you of that, let me show you the data. So, okay, so I need to just tell you a bit more and then I'll come back. In fact, this is better. So here, this is the bow shock, and there is then this other boundary, which we call as the magnetopause. I'm going to tell you why it is called magnetopause in a moment. But the region between the bow shock and the magnetopause is called the magnetosheath. And this is the region that I'm interested in. The example that I have chosen is from this region. Magnetopause, it is called magnetopause because the dynamic momentum of the solar wind is balanced by this Earth's magnetic field right at this point. That is why it is called a pause. It means they are exactly in balance, and that is why this term magnetopause. Magnetopause, from those of you who are familiar with the shocks and discontinuities, it's a tangential discontinuity, and it means that no mass transport can occur across the boundary. But I'm going to show you how this happens in a moment. So the next thing that I would like to tell you is the following. Actually, I need to keep going for. So the region before the bow shock is called the upstream region. The region after the bow shock is called the downstream region. now the shock I've told you does three things. It increases the density, it increases the magnetic field, and it brings the velocity of the structure down. And I will just tell you, so there is this upstream region. You see the number density has gone up, the magnetic field has gone up, and the velocity has come down. So what I was telling you, it exactly does what you expect from the Rankine-Hagonic condition. This is the power of these conservation laws. Just the fluid equations coupled with the Maxwell's equations, they tell you this is what a shock should do, and this is essentially what it does. And now this downstream region, because the number density has gone up and the temperature has gone up as well, so it means that this has become a more disordered state. So both the things are coined, the upstream region and the downstream region, before and after the shock, it is called, or it is called the low entropy region and the high entropy. Before the shock, it's cooler, density, the temperature has not gone up. After the shock, density has gone up, the temperature has gone up, and only the solar wind velocity has gone down. So that is why it is called, the magnetosheath is also called the high entropy region. And because I'm going to show you some wave in the magnetosheath, so that is why the title, that I'm going to tell you something about the fourth state of matter in the high entropy region of the terrestrial. All right, so coming back, so there are a few details that I'm going to skip now because then I'll take more time. That is this equation that I showed you, that when I come across a boundary, which is like a magnetopause, then the diffusive term takes over. So the idea is that when the magnetic field lines of the Earth goes southwards, and northwards, because if you see magnetic field lines can go from south towards north, and the interplanetary magnetic field is such that it is northward bound, and there will be a curl of magnetic field, and it will give rise to a current layer, and that current layer will, for a short time, allow the charged particles from the sun side to go onto the earth side, and from the earth side to go onto the sun side. So this process, which makes it happen, is called the magnetic reconnection. And this magnetic reconnection makes discontinuity which doesn't allow the mass transport. It allows it to happen. So I'm not going to into the details of, and I'm going to skip certain details because how much time do I have? 10 minutes? 5 minutes. I have to rush. So just to tell you that cluster spacecraft is the joint NASA-ESA program which roams about space, and it is basically designed to study the solar wind, the magnetosheath region, and the region which is around the Earth. Let me show you this. So all these regions which are represented here, and they are named here. So this region is where the tail is going forward. The solar wind drags the terrestrial magnetosphere forward, and it's called the magnetotail. So all these regions are studied by the cluster spacecraft. And so now I go to the problem. Cluster is very important because in the past we just had one spacecraft, and one spacecraft cannot resolve the spatiotemporal ambiguity. What I mean by that is, if you have just one spacecraft, at some point you just cannot differentiate between whether a change is spatial or temporal. For that, you need to have at least two spacecrafts, one placed in the solar wind, the other in the magnetosheath, to know whether something is happening because the sun is active, or something because of the essential inhomogeneities in the magnetosheath structure. So cluster spacecraft was, and then on top of that, you know that the 3 points define a plane, but for 4 points, you can have a three-dimensional structure. So cluster can be maneuvered in such a way that it can have a 3D structure of all these things in a tetrahedral shape. Okay. So moving on, just to tell you, there are lots of instruments placed on the cluster. I am just going to be interested in the piece, which is the plasma electron and current experiment. And okay, so these are the magnetic field structures. And if you want to know what they mean, so I can tell you that when the sudden magnetic field suddenly goes up, that is where the shock or the solar wind enters the magnetosheath, because there is a sudden increase in the magnetic field, and we know that is associated with the entrance in the high entropy region, that is the magnetosheath. So even by looking at the magnetic field structure, you see it is relatively calmer initially, but then it becomes very wibbly wobbly. So it has to do with something which has to do with the shock normal and the magnetic field. Well, I don't want to bore you with all those gory details, but what I want to tell you is there's a lot of physics behind it, and by looking at the magnetic field structure, you know where the spacecraft is, what it is telling us, which region it is in. So there is a lot that it tells you. All right, so we try to study what we practically know as Whistler waves with temperature and isotropy. They have a frequency around 100 hertz. And when they are looked in the magnetosheath, they are called the lion roars, because when played through a speaker, it appears as if the lion is roaring. So again, so I don't want, because Rizwan has told me the time is very short. So I'm just going to tell you that these red wiggles here in this frequency panel, these show the lion roars. And we did some theory and data, but we found out that there were times when the theory and data agreement, we did kinetic theory for electrons, and we assumed that electrons follow the Maxwellian distribution. And we didn't get a good, agreement at certain places, and there were certain features which could not be explained through the theory that we employed. Why was that? Because what we observed was, let me go further, in fact. So this is the paper by us, which shows that how does the electron distributions downstream of the bow shock look like. They appear to be flat top. So it means that we employed a theory where we assumed electrons to be Maxwellian, whereas they were actually flat top. Why they are flat top? Maybe in the question and answer session, I will explain it to you. At the moment, I'm just skipping it. I'm just telling you that then my collaborators, almost 16, 17 years ago, I was then a PhD student. My supervisor at Imperial and my supervisor here in Government College University, they wrote a paper and they came up with this distribution function, which produced a flat top distribution with a non-Maxwellian feature at the tail, and with two parameters R and Q, where R fiddles with the behavior at the low energy end, and Q fiddles with the high energy distribution. So, and in the limiting cases, it reduced to the so-called kappa distribution and the Maxwellian distribution. And we employed the kinetic theory again. And after almost 8 years after we wrote the first paper, we showed that the features which could not be explained, as you can see, there's a lot of, horrible looking mathematics involving the, a lot of integrals and notations. We found out that the agreement of the theory is much better, and we could explain the unexplained features in the Maxwellian distribution. And quickly tell you, the final comment was that in the Maxwellian theory, the condition that we found out for the wave growth was this, but then when we did it using the real distribution, which is observed, which is the flat top distribution, we found that there is another condition which needs to be met. And when those conditions were met, then actually we got better, agreement, not only with the linear frequency, but also with the growth rates of the waves and a closer match, and those features which could not be explained with the non-Maxwellian, with the Maxwellian electron distribution, it could be explained. And why electron distribution? Because we were looking at the Whistler waves, which are electron, we are looking at the electron whistlers. There are ion whistlers as well, those who know the subject. but we were looking at the electron time scale. We were looking at the electron visitors. Lion rows are electron visitors, and we showed that there's a much better agreement with theory and data. So this is a great success story, and it also tells you that sometimes your assumptions like Maxwellian distribution is easy to handle. We know the integrals and all that, but we need to work harder to get a closer agreement with nature. Because what data tells us is how the nature behaves. Theory is just an approximation. Even RQ distribution, is just an empirical fit. It doesn't have a thermodynamical basis, but yes, we fitted using the data sets that we had from the cluster data, and we found out that the agreement with between theory and data is very good. So thank you very much. I had to skip many details. Maybe in the question and answer section, you will ask questions, and I'll be able to reflect on the things that I skipped very quickly. Okay, thank you. Thank you very much.
Yeah, there's a great talk, Waqas. Yeah, and quite easy to, in easy term, you explain very difficult concept. So the floor is open for questions. So anyone who wants to ask questions can raise the hands. There's an option of raising hands. So yeah, you can ask questions now, please. Okay, so there are a couple of questions in the question and answers one.
Okay.
So yeah, so Awais is asking that are the coronal mass ejection and corona effect are the same thing or are they different?
No, coronal mass ejections, like you see something coming out of the sun. Corona is the outermost layer. The coronal mass ejections that is what you see happening at the surface of the sun. And this is because of extremely turbulent conditions inside the sun. So basically, these are all exhibitions of magnetic turbulence and extreme temperature gradients. And so like it's a kind of a redistribution of energy and momentum in a very short time. And these events are called very violent events because there's a lot of mass ejection also. So yeah, and during coronal mass ejections are also related to the geomagnetic storms. I didn't broach the topic because the time was too short. It's a very vast field, and I just introduced you to the very basic stuff.
Okay.
Corona is just the outer. There's no coronal effect. So as such, there is no coronal effect. There are coronal holes. There's coronal mass ejections. Coronal holes. These are the stuff near the poles, and that is where the fast solar wind comes from. So I've told you the slow solar wind comes from the equator, but the fast solar wind comes from they are supposed to be coming from the coronal holes near the poles.
Okay, yeah, thanks. So I hope it would answer his question. There's another question from Mudassir Shah, a slightly different one, although not topic of this talk. But he says, in how many ways can one confine plasmas?
One can
confine plasmas.
Well, he knows much better than me, but I know magnetically confined fusion and inertial confinement fusion. These are the two ways that you can confine a plasma.
Yeah. Okay. Yeah. Okay. So this line roar phenomenon you said, is it just like you said is mainly because of the viscosity of electrons which comes into play, or is it some non-linear effect?
No, it is because of low. Yeah, thank you very much for asking this question. Now we need to understand why is this wave generation. Wave is always because of some disturbance in the medium. So now I told you that this is Whistler waves with electron temperature and isotropy. So when you have a magnetic field, naturally two directions are introduced. One along the magnetic field and the other perpendicular to the magnetic field. So there's a temperature perpendicular in the perpendicular direction, and there is a temperature in the parallel direction. So it means that the parallel and perpendicular temperatures are not the same. Because of that, because there is a gradient, and nature wants to, just restore the equilibrium posture. So you need to kill the gradient. In order to kill the gradient, there will be, an instability there, and that instability will give rise to this wave. So had there been no temperature anisotropy, there would have been no Lion row. So you ought to have some free energy, and for that free energy, basically makes you drive a wave in a medium, because the whole idea of the instability is to suppress that gradient, to ward off the gradient. But there is a pumping mechanism inside the magnetosheet. So that's why you see Lion rows all the time. Nature tries to kill the gradients, but these gradients keep coming up. So we tried to answer that question later. We found out that the magnetic moment conservation is not the reason. This is still an open question. What is the pumping mechanism that keeps pumping energy to the perpendicular electrons so that this perpendicular anisotropy is maintained, and we keep observing the Lion rows.
Okay, yeah, that's great. Okay, I have another question, but let's Zain, you want to ask a question? Zain, another participant. Hello.
Can I ask? I want to answer Asif Zaman's question. He said that it is easy to visualize the 3 plasma conditions for kinetic model. How can we visualize these conditions for fluid model? Well, the conditions are for a plasma. It's not for a fluid or a kinetic model. If you are saying I'm talking about a particular model of a plasma, then plasma ought to meet those 3 criteria. You can't say that a kinetic plasma will have a different criteria and a fluid plasma will have a different criteria. No, plasma is plasma, and it ought to meet the fundamental criteria in order to distinguish it from an ionized gas.
Okay, there is another question from Akmal Danish. Is there any theory which defines the high temperature of corona?
Well, yeah, so this is an anomaly. Generally, you expect the inside layers to be hotter than the outside layer, but corona is hotter. And so all the theories are out there in the market, but the one which has become most popular is what we call as the Alvin cascading. So it's the Alvin waves, and they cascade, and that is why the corona is hotter than the photosphere. I've not worked on the subject, but I know, yeah, this is a corona problem, and people have come up with the answer that it's the Alvin wave. Again, it's wave particle interaction. A lot of convection happens, and convection happens at a rate that the corona becomes hotter than the photosphere.
Yeah. Okay, yeah, Zain, you have a question? You go ahead. You are unmute now, so unmute yourself and ask the question if you have. We can't hear you. Maybe. Okay, I don't know. Maybe you can write your question in the Q&A section, and we can try to answer.
Yeah. They can write it here. Yes. It's right in front of me. I can see them.
So.
देर में कोई और सवाल कर लें
जी कोई भी
सरमद से अगर सरमद हैं तो उनसे मेरा पहले ही बहुत ज्यादा जो है वो मैं उनसे एंड अपॉलॉजी के मेरा ख्याल था कि बहुत सी चीजें because I've been doing plasma physics for the last 20 odd years, so sometimes you think this is something that you can explain, but when you begin to explain, there is a lot of jargon of the subject that you need to cover, and then you run short of time. In the end, I have to actually, tell things in a very quick manner.
Yes. So Tajammul Khokar is asking, for unmagnetized case, we can't take temperature anisotropic.
Yeah, because magnetic field introduces the temperature anisotropy. Otherwise, you don't have those 2 directions. Magnetic field introduces a natural ordering. You have a perpendicular. Otherwise, if you talk about perpendicular and parallel, it doesn't really make sense, because parallel and perpendicular refers to the fact that you have motion along the field and you have motion perpendicular.
Okay, Waqas, this is Sarmat. So the host asked me to say something. So I can't ask any specific questions because, this is high-powered physics and applied math. And, I'm more of a discrete mathematician. So nevertheless, it was interesting to listen to you, and it was very nice. And, so that's it. Thank you.
Thank you very much. Thank you.
Okay. Yeah, so I don't see any more questions. So
Asad, there's one more question.
Kahiye, yes.
This was a question coming in from Mohammed Daud Wad. I had promised him that we would take it up at the end of the talk. The question is, could quantum field theory be applied to a plasma?
Yeah, yes, it can be applied to a plasma when you look at the quantum plasma. So well, if you're dealing with quantum plasma, so yes, quantum field theory can be applied over there.
Right. I'd just like to add that in particular, there is a thing known as a quark gluon plasma.
Yes.
Where.
Yeah. No? Yes, there's a quark gluon plasma, of course, but that is particle physics. Zanali has asked a question. I have a question related to linear, quasi-linear, and nonlinear theory. Quasi-linear has to do with space. No, Zan, quasi-linear theory actually takes into account what happens when the wave-particle interaction takes place. So now, if wave has imparted energy to the particles, I've just talked about the distribution function, the perturbed distribution function F1. But I've not talked about F0. What has happened to F0? How it has evolved? So quasi-linear theory, talks about that. What happens to the background distribution function? As far as the nonlinear kinetic theory, even in the quasi-linear theory, you don't deal with the the terms where the fields get multiplied in such a way that you have to take the nonlinear effect of the fields. In mathematical terms, there are certain couplings that you don't take into account. But in the fully nonlinear theory, and I don't know, maybe 7 to 10 people in this around the globe might be doing nonlinear kinetic theory. I have not read too many papers about nonlinear kinetic theory, So one paper by Peter Yoon, because he worked for good 10 years and then he came up with some explanation of the kappa distribution using the nonlinear kinetic theory. Apart from him, I do not know of anyone. The great Russians, of course, they are the giants. They did a lot of nonlinear theory. They write books in language which ordinary mortals like me cannot access. But I hope before I die, I'll be able to make some sense out of it at some point.
Okay. Yeah, Waqas, Adam is asking Adam Zaman ki, because a lot of students are attending this talk. So can you suggest maybe recommend some introductory books on plasma physics that might be helpful for the students?
Yeah. So I mean, my personal favorites are Boyd and Sanderson. These are the authors. Maybe Plasma Physics is the name, or Fundamentals of Plasma Physics, something like that. There is a book by Balin. And then there is a lovely book by Physics of Space Plasmas by G.K. Parks. Then there is another lovely book by a very good space physicist, Bhattacharya, and what's the other name? It's basic space plasma physics. So if you just type in Bhattacharya, you will see the title of the book. Chen people employ, but Chen is a an experimental physicist. So many things that he explains. Bennett and Bhattacharya, so Bennett and Bhattacharya. Thank you. Somebody has just told me that. Thank you very much for reminding me. So I'm very poor with names, but I shouldn't have forgotten Bennett. He's a big name. So anyway. Physics of Plasmas is a good, book. So Introduction to Plasma Physics with Space and Laboratory Applications. Yes, that is precisely the title of the book.
Okay, yeah. So
And
another
plasma is,
question.
I mean, it's something. It's although I don't know why sometimes people say that well, it's just the fluid equation and the Maxwell's equations, but in order to fully appreciate it, you ought to know that it's all an approximation game. Sometimes you are at ion time scale, the other times you are at the electron time scale, and then you need to have a physical feel of things, what is happening. For instance, if you just look at the instability and you don't understand that there is a temperature gradient and what does it mean, it's the system, deviated from equilibrium, it wants to restore its quasi-neutral posture. That's the nature's way of, killing the gradients. So then it makes it quite interesting, actually.
Yeah, another question Adam has asked, can you highlight a couple of biggest problems in the field which are currently being tackled? So just to...
Well, fusion physics, I don't do fusion physics, but ITER is trying to, come up with an answer of using this infinite source of energy, which is water, using fusion, so that's the biggest. That's not really a scientific problem, it's a technological problem. Otherwise, if you ask me, then of course there are things like, there's a question that solar wind comes out, but it goes on and still remains hot. So what are the mechanisms that keeps it hot, So these are kind of questions that are still open. The solar wind termination shock, a few observations have been made by Voyager 1 and 2. So those are the questions that need to be answered as well. And then, of course, a lot of stuff that we need to do regarding the nonlinear structures, because what I have shown you is just the linear kinetics, the linear wave analysis from the kinetics perspective. Now there are, from the fluid perspective, there are shocks, solitons, vortices, and how you will, handle them in data. So how will the data analyst express them, and how can you then do a similar kind of theory and data agreement? So these are the things that can be done. So these are like, and then generally there are a lot of approximations. We ignore certain terms and we keep certain terms. So it's always an approximation of reality. What if you, retain everything and you try and solve it? So then it becomes a gigantic problem. Turbulence is mostly understood through numerical simulations, but if you ask me theoretically, well, not many papers that make you understand the turbulence. Chaos is another field, people try and understand, but again, it is largely unexplored. What are the, manifestations of chaos in data? That's another question. I would like to see data handlers, looking at the exhibition of chaos in the system, stuff like that.
Wonderful, Waqas. There's excellent array of problems you have highlighted. So I see no more questions. So yeah, we would like to thank you again for this wonderful talk and introducing us to a topic which we don't normally usually hear much about, because none of us is a plasma physicist in our department, at least. So yeah, thank you again for
thank you very much. Thanks for bearing with me.
Yeah, it was really a pleasure. Yeah.
So I wanted to just add one thing, so there were a couple of suggestions. One is, Waqas, if you could write some of these resources, the books and those titles, because once we go away, right, those things are lost. Typically, we don't save the chats and all that. So if there's like a post-talk email in which, the resources or maybe interesting pointers that you can give, that would be very nice. The other thing would be very nice is if I could see the list of participants, because I can only see you, and it's just sort of makes us feel better that there are other people, right? And it's just this is just like as if I'm the only one sitting here and Waqas is the only one. So these were two suggestions.
That's not a bad prospect. And I always thought you were a loner. I never thought you were such a gregarious animal.
Well,
yeah.
So are you in Islamabad?
Yeah.
Oh, I thought you were in Lams and we could meet, but.
Oh yeah, no. But I'll let you know beforehand when I, come to Lahore next time. Yeah.
Thank you, guys.
I look forward to seeing you.
Okay. Yeah, thank you. Thank you, Sarmat, for pointing out. We will definitely take into account these.
Yeah,
two
I'll make a
suggestions
list
of
and I'll send it to you. I'll send it to Rizwan and he can share them. Yeah.
Yes,
Samad
yes,
has made a very valid point. Sometimes
yes.
we, listen to something, we think that we are going to remember, but we immediately forget.
It's not. Yeah.
2
that's
days
true.
down the line, we will,
Mm.
have no idea what was talked
Yes.
about, what was the book he
Mhm.
referred to, that's all.
Yes. Yeah. Yeah. We will share it with the student or with the participants. We do have a list of participants which is automatically saved, so we can share it. Yeah.
Okay.
Yeah.
Thank you, guys.
Thank you.
Yeah.
Thank you.
Thank you. Thank you.
Okay.
Thank you, Waqas, again. So yeah.
Pleasure.
Okay.
Pleasure.
Yeah. Allah Hafiz to everyone. Ji.